Deep inside a Martian core sample, researchers found molecular fingerprints that weren't random chemistry. They showed chirality, the same-handedness rule followed by every living thing on Earth. Even more shocking, those molecules formed complex DNA-like structures, the kind of chemistry that doesn't just happen by accident. If life really did spark on Mars, where did it go? Was it wiped out, or could something still be alive, buried beneath the dust, waiting? Let's dive into. NASA's Perseverance rover touched down on Mars with a mission that seemed straightforward: search for signs of past life. It was the first step in a multi-billion-dollar effort to one day return Martian rock samples to Earth. But what Perseverance uncovered surpassed every expectation and challenged long-held assumptions about our planetary neighbor. Operating in Jezero crater, a 28-mile-wide depression thought to be an ancient lake bed, the rover spent months drilling, sampling, and photographing the terrain. Its ability to maneuver across rugged landscapes and collect meticulous data already impressed scientists. Then came the unexpected. A routine sequence of readings, images, and chemical tests suggested something beyond sediments or fossilized microbes. Beneath layers of iron-rich dust and oxidized rock, Perseverance detected molecular signatures that hinted at processes far more profound than geology alone. The breakthrough came from a core drilled near a site labeled Sector Delta 9. At first, the material appeared to be another clay-rich deposit. But analysis revealed something extraordinary. Embedded within the sample were complex carbon chains. These weren't common organic fragments. They were structured macromolecules, rare in extraterrestrial environments and strikingly consistent with biological synthesis. Their repeating patterns and polymer complexity resembled what on Earth could be considered a primitive precursor to DNA or RNA. The revelation deepened with spectrometric analysis. The molecules displayed chirality, handedness, a universal trait of life on Earth. Amino acids and sugars in living systems show consistent left or right-handed orientations, an asymmetry not expected in random chemistry. Yet Perseverance's samples displayed a slight but measurable bias in molecular chirality. They weren't evenly distributed but leaned subtly in one direction. Such asymmetry is extraordinarily difficult to explain without invoking biological processes. It was not merely chemistry frozen in time, but a molecular fingerprint of selection, possibly reproduction. In that moment, the interpretation of Mars shifted. These findings suggested more than habitability; they pointed to the memory of something once alive. The discovery reshaped not only the mission's trajectory but also humanity's understanding of life beyond Earth. The implications struck the scientific community with force. The discovery suggested that early Mars was not just habitable but potentially biogenic. If confirmed, this transformed Mars from a planet with water into one that may have once hosted a complex biological ecosystem. Following the chemical revelations, Perseverance's microscopic imaging zoomed in on the core sample. What emerged were fractal-like formations arranged in filaments, echoing microbial mats from Earth's most extreme environments: hydrothermal vents, subglacial lakes, and deep-sea crusts. They were not fossils in the usual sense, but molecular imprints bearing the unmistakable residue of life-driven processes. The finding unsettled planetary science. Earth had long been considered the unique cradle of biochemistry, blessed with the right distance from the sun, magnetic field, geology, and atmosphere. Mars, by contrast, seemed a less likely candidate, limited by its weak magnetosphere, thin atmosphere, and frigid climate. Yet the evidence pointed to a once thriving chemical environment capable of producing and perhaps sustaining life for significant stretches of time. What astonished researchers most was the convergence implied by the molecules. They showed structural similarities to Earth-based counterparts, yet diverged enough: chirality, bonding angles, functional groups, to suggest an independent origin. This was not contamination, nor was it panspermia in its traditional sense, life seeded from Earth or beyond. Instead, it hinted at parallel evolution at the molecular scale. Nature, it seemed, had discovered more than one pathway toward life. The consequences reached far beyond Mars. If life can arise independently in two places within the same solar system, then the odds of it existing elsewhere rise dramatically. It may dwell beneath Europa's ice crust, in Titan's methane lakes, or in Enceladus's hidden oceans. Even the Drake equation, once reserved for estimating the number of civilizations, demanded revision. Its scope now extended not just to intelligence but to life in its earliest forms. Perhaps the most unsettling aspect was not scientific but psychological. For centuries, Mars symbolized mystery and distance. With this discovery, it became a mirror. Its organic residues felt less alien than familiar, as if Mars were a sibling planet, one that began the same story but was cut short, frozen in youth by planetary misfortune. Perseverance has uncovered a wide range of rocks and soil layers that reveal Mars' volcanic and watery past. Equipped with SuperCam, a tool combining a camera, laser, and spectrometers, the rover can study rocks closely and determine their composition. Its analysis revealed volcanic rocks, evidence of ancient eruptions that once reshaped the Martian surface. Studying them helps scientists reconstruct when and how volcanic activity occurred. Alongside these, sedimentary layers appeared, formed by flowing water that left behind sand and mud, later compressed into stone. Each layer acts like a page in Mars' geological record, preserving stories of rivers and lakes that once existed. As instruments were recalibrated for more precise targeting, Perseverance made an even more striking find. Within calcite veins and hydrated silicates, it detected polycyclic aromatic hydrocarbons. While PAHs can form without biology, the structures here, complete with alkylated chains and selective isomers, mirrored those produced by microbial decay on Earth. Their clustering in low-lying troughs, places once filled with water, echoed microbial bloom decay zones seen on Earth's seafloors. The terrain around Delta 9 grew richer in meaning. Sedimentary layers displayed ripple patterns pointing to slow-moving currents, perhaps tidal. Clay deposits showed alterations requiring long-term exposure to slightly alkaline water. Together, these features suggested a once stable aquatic environment capable of supporting complex chemistry. Mineralogy painted the picture of an ancient oasis, with warm waters and chemical gradients ideal for molecular assembly. Supporting data on atmospheric composition, magnetic field reversals, and isotopic ratios indicated that Mars once had a thicker atmosphere, likely rich in greenhouse gases, allowing liquid water to persist on the surface. Though this hospitable period may have lasted only tens of millions of years, it was potentially long enough for intricate organic processes to take hold. What Perseverance revealed was not a barren rock but a planet that had been dynamic, with water, active geology, and the ingredients necessary for life's emergence. If you like this video, be sure to subscribe and hit the bell so you don't miss any future episodes. Don't forget to share it with your friends too. It helps the channel out, and I'm excited to continue bringing you more awesome content. But where could that Martian life have gone? Mars is quite inhospitable on the surface today, but what about underground? Just like Earth, Mars could have layers beneath its surface where tiny life forms found a safe place away from the freezing temperatures and radiation on the surface. These hidden spots could have had everything tiny microbes needed to live, like water and food from chemical reactions, even without any sunlight. On Earth, we find life in some really unexpected places, like at the bottom of the ocean or in the hot springs of Yellowstone Park. These creatures don't rely on sunlight. Instead, they get their energy from chemicals in their environment. Scientists believe that if there was life on Mars, it could have survived in similar underground locations, feeding on chemicals from rocks. This idea isn't just speculation. It's based on real science. Researchers have been studying places on Earth where life survives in extreme conditions and are using what they've learned to figure out where we might find life on Mars. The idea that there could be a deep biosphere on Mars, similar to the deep, dark places where life lurks on Earth, is a game changer. The evidence pointed to ancient hydrothermal activity. Long ago, geothermal heat from volcanic hotspots may have warmed subsurface water, creating the perfect crucibles for microbial development. Mars may not have had one genesis site. It might have had thousands spread across its ancient seafloors and buried riverbeds. This idea opened an entirely new paradigm. Until now, humanity had been bound by the assumption that a planet needed an enduring surface biosphere to support life. Mars suggested a different story. that life could rise and fall within a short planetary window, confined to subsurface refuges and chemical microniches. These environments may have been out of sight, but they were rich, potent, and dynamic enough to generate complex organic evolution before vanishing into geological silence. But here's the terrifying question that haunts every scientist studying these findings. What if life didn't completely vanish? What if it retreated deeper underground, adapting to the harsh conditions, evolving in isolation for billions of years? The isotopic skew wasn't confined to a single spot. It extended in radial patterns that hinted at diffusion from a central source, perhaps a once thriving microbial hotspot or even a vast underground aquifer system. If Mars harbored life in its subsurface, that life could still be there, waiting in the darkness, possibly evolved into forms we can't even imagine. This means life could exist in places we've never considered before, both on Mars and on other planets throughout the universe. In the vast expanse of Mars, UFO enthusiasts believe they have found groundbreaking evidence, a circle of stones arranged in a ring, which they call Marshenge, after Earth's Stonehenge. This supposed structure has fueled debates and theories. Some claim it could be the remains of an ancient Martian society, perhaps even linked to early Earth cultures or visitors from beyond. To them, Marshenge represents a possible clue to a lost civilization, sparking speculation about life that may once have existed on Mars and whether it had contact with our planet. Not everyone is convinced. Scientists and planetary researchers remain highly skeptical. While the stone circle is intriguing, they argue it is not evidence of a Martian Stonehenge, but more likely the product of natural processes. Other enthusiasts point to NASA photos showing shapes they say resemble pyramids, statues, and even faces. They argue these formations are too precise to be accidental, interpreting them as remnants of buildings or art from an intelligent Martian past. These claims have generated widespread discussion and fascination. The scientific community, however, offers a different explanation. Mars has been sculpted by wind, erosion, and shifting sands over millions of years. Natural processes can create shapes that appear strikingly familiar to us. Researchers often cite pareidolia, the brain's tendency to see recognizable patterns like faces or animals, where none exist. It is the same phenomenon that makes us see shapes in clouds. To scientists, these so-called pyramids or faces are simply rocks and shadows, not proof of lost civilizations. While surface formations capture public imagination, the most compelling discoveries are hidden beneath Mars soil. Perseverance has detected organic compounds and chiral molecules, chemical signatures far more persuasive than stone circles or rock faces. These molecular traces suggest that Mars once held the conditions necessary for life, so providing stronger evidence of its potential past biology than any surface structure could offer. Leading the exploration of Mars are NASA's rovers Curiosity and Perseverance. These robotic explorers are packed with advanced instruments designed to study the red planet in unprecedented detail. Curiosity, part of the Mars Science Laboratory mission, landed in Gale Crater in August 2012. Its main goals were to determine if Mars could ever have supported microbes, to study the planet's climate and geology, and to collect data useful for future human missions. Over the years, Curiosity has uncovered strong evidence that rivers and lakes once flowed across Mars. It has detected chemical building blocks of life and seasonal variations in the atmosphere, all suggesting that Mars may once have been habitable. Perseverance, the newer rover, landed in Jezero crater on February 18, 2021. Scientists believe this region once held a lake, making it an ideal place to search for signs of past life. Perseverance's mission is to look for biosignatures, study ancient Martian environments, and collect rock and soil samples for possible return to Earth. The rover also carries groundbreaking experiments. MOXIE, a device that extracts oxygen from Mars' carbon dioxide-rich atmosphere, is a first step toward enabling astronauts to breathe and produce fuel on Mars. Perseverance also deployed the Ingenuity helicopter, proving that controlled flight is possible in the planet's thin atmosphere. Together, Curiosity and Perseverance act as the eyes and hands of scientists on Mars. Curiosity continues to study Gale Crater's ancient environments, while Perseverance actively searches for direct signs of biology in Jezero crater. Their combined discoveries offer a fuller picture of Mars' history and habitability. the data has already reshaped our understanding. Curiosity's detection of seasonal methane hints at active geological or even biological processes. Perseverance's discovery of organic molecules showing signs of chirality, the molecular handedness associated with life, represents the strongest evidence yet that Mars may once have hosted living systems. These rovers are humanity's most advanced tools in answering a fundamental question: are we alone in the universe? Each image, sample, and measurement they send back brings us closer to uncovering Mars' secrets and preparing for the day humans set foot on its surface. The selection of Jezero crater as Perseverance's landing site wasn't random. Scientists spent years analyzing potential locations, and Jezero emerged as the most promising site for finding evidence of ancient life. This 28-mile-wide crater contains some of the most well-preserved evidence of ancient water activity on Mars. Billions of years ago, Jezero crater was home to a large lake fed by rivers that carved channels still visible today. The crater contains a river delta, where sediments and potentially organic materials would have been deposited over millions of years. If life ever existed on Mars, Jezero crater would be one of the most likely places to find evidence of it. The way Perseverance landed on Mars is just as fascinating as where it landed. NASA used a special system called the Sky Crane to gently place the rover on the ground. This wasn't a typical space landing. First, the spacecraft carrying Perseverance quickly entered the Martian atmosphere. Then, it used a huge parachute to decelerate while it was still high in the sky. But the really incredible part came next. Instead of landing on wheels or legs, Perseverance was carefully lowered to the ground by a type of flying crane with rocket engines. This Sky Crane carried the rover to its landing site, and once the rover touched down, the crane flew off to land in a safe location some distance away. This incredible technology was first used with the Curiosity rover, but for Perseverance, it was refined and improved to handle the rugged terrain of Jezero crater. This method is amazing because it allows scientists to land rovers in much more interesting and much harder to reach places than before. Before Sky Crane, landing sites had to be wide, flat, and somewhat boring to avoid accidents. But now, with this new technology, we can land in places that are much more exciting for science, like Jezero crater with its cliffs, dunes, and boulder fields. The success of Sky Crane shows how smart solutions and bold engineering can open up new possibilities for exploration. Thanks to this technology, Perseverance could begin its mission right in the middle of a fascinating landscape immediately after landing. The rover found itself surrounded by the geological history of Mars, with ancient river channels, delta formations, and sedimentary deposits, all within reach of its sophisticated instruments. As Perseverance began exploring Jezero crater, it became clear that the site selection was even more prescient than scientists had hoped. The rover's early discoveries of organic molecules and complex carbon structures validated the decision to land in this ancient lake bed. The crater's unique geology had preserved a record of Mars' past that might have been erased elsewhere on the planet. The international scientific community was thrown into coordinated motion following Perseverance's groundbreaking discoveries. Data-sharing pipelines between NASA, ESA, JAXA, and other space agencies were activated at an unprecedented pace. Robotic missions that had long been theoretical gained immediate priority and funding. Orbiters already circling Mars began fine-tuning their spectral analyses to scan for similar patterns across other crater lakes, including Gale, Eberswalde, and Holden. It became clear that Jezero might not be unique. If other deltas harbored similar structures, it would mean Mars wasn't simply lucky. It had been systematically habitable in its past, possibly planet-wide. Simultaneously, Perseverance's drill moved deeper, inching its way toward older sediment layers untouched for eons. The deeper it went, the more compelling the narrative became. Anomalous isotopic ratios of nitrogen and sulfur started appearing. These isotopes, particularly the lighter variants, are key indicators of biological processing. On Earth, microbes prefer lighter isotopes for metabolic reasons, leaving behind signatures that geologists can identify even after billions of years. The presence of similar signatures on Mars pointed to the existence of comparable selective processes. Again, not definitive proof of life, but a chemical fingerprint that implied biological activity had once influenced the soil composition. What made this discovery even more unsettling wasn't just the depth of the findings, it was the breadth. The isotopic variations weren't confined to a single spot. They extended in radial patterns that hinted at diffusion from a central source, perhaps a once thriving microbial hotspot or even a vast underground aquifer system. NASA's high-gain antennas continued to stream a flood of data back to Earth. Dozens of laboratories worldwide began modeling the organic structures discovered, trying to simulate their formation under controlled conditions. It wasn't just about confirming what Perseverance had found. It was about understanding how such complexity could arise in a Martian environment. The implications extended far beyond Mars. If life could emerge independently on two planets within the same solar system, it suggested that life might be a common occurrence throughout the universe. Astrobiologists began revising their estimates of potentially habitable worlds, and the search for life expanded to include moons like Europa, Enceladus, and Titan. Beyond the ongoing successes of Curiosity and Perseverance, NASA's long-term plans for Mars are ambitious. The most significant effort is the Mars Sample Return Program, aiming to bring back the samples Perseverance is collecting, possibly even those from Curiosity. The mission involves sending a lander to retrieve the samples, launching them into orbit, and transferring them to an orbiter for return to Earth around 2033. It will be the first time Martian material is deliberately delivered to terrestrial laboratories. This mission is crucial because while rover instruments are advanced, Earth-based labs can conduct analyses far beyond what can be done on Mars. Using mass spectrometers, electron microscopes, and other powerful tools, scientists will be able to examine samples at the molecular level, potentially confirming or refuting the biosignatures already hinted at by Perseverance. In the meantime, the rovers will continue their work. Curiosity has already found evidence of ancient water and studied Mars climate, while Perseverance is actively searching for signs of past life. Together, they will keep building the foundation for the next stage of exploration. But Mars exploration doesn't stop with sample collection. The larger vision is human exploration and eventual settlement. NASA views its Artemis program, returning humans to the Moon, as a stepping stone. By building a sustainable lunar presence, NASA can test the life support systems, radiation shielding, and resource utilization technologies needed for a Mars mission. SpaceX, led by Elon Musk, has its own bold timeline. Musk envisions self-sustaining Martian cities, complete with farms, infrastructure, and communities. Starship, the spacecraft under development, is designed to carry large numbers of people and cargo, and its reusability could make frequent trips to Mars financially feasible. Musk also proposes using Martian resources directly to produce water, oxygen, and building materials, reducing reliance on Earth. Creating such a settlement would mean developing methods to grow food in Martian soil, generate power through solar or nuclear systems, and build habitats from local materials. However, recent discoveries of organic molecules and possible biosignatures raise an added challenge. The colonization must be pursued carefully to avoid contaminating or destroying potential Martian ecosystems. NASA, SpaceX, and international partners are working together on these challenges, building the technology and strategies needed to ensure that when humans finally land on Mars, they will be prepared not just to visit, but to stay. Perseverance's discoveries have reshaped our understanding of life in the universe. The molecular fingerprints within Martian soil, chiral molecules, complex organics, and isotopic signatures echoing Earth's biology suggest Mars was once a cradle of chemistry organized enough to sustain life. This evidence challenges the view of Mars as a barren world, pointing instead to a planet that may have once flourished with biology. What do you think about these groundbreaking discoveries? Could Mars still harbor life in its deep underground biosphere? How will this change our approach to exploring and potentially colonizing the Red Planet? Share your thoughts in the comments below. If this video opened your eyes to the incredible possibilities that exist right in our own solar system, make sure to like and subscribe for more mind-bending discoveries about our universe. Thank you so much for watching, and we'll see you in the next video. Thanks for being with us. Leave a comment, like to show your support, and remember to hit that subscribe button for more exciting videos. See you next time.